The moment you hit enter, a physical signal travels from the key through the copper traces of the motherboard and launches into the network. The problem is a basic language barrier. We navigate the internet using human-readable names like Coursera.org, but network hardware only understands numbers, specifically IP addresses. The machines need a numerical destination to route your traffic. To bridge that gap, your computer dispatches a specialized courier known as a DNS query. This small packet of data has one job: find the specific numerical translation for the name you just typed. While this happens in the background, network administrators watch these couriers constantly. Using terminal tools like dig or NSLOOKUP, they can inspect the query's path, verify IP mappings, and check remote mail servers in real time. There is no single centralized database holding all the world's IP addresses. Instead, that information is scattered across millions of independent servers, meaning our courier must navigate a highly distributed global network in a matter of milliseconds. The packet first arrives at a local DNS resolver, usually managed by your ISP. This starts a recursive query, where the resolver takes full responsibility for finding the answer on your behalf. If the resolver doesn't have the answer stored, it begins an iterative query. This is a step-by-step interrogation, where the resolver bounces across the internet, asking different layers of the hierarchy for directions. This diagram shows DNS's hierarchical database. The resolver queries the root servers, which direct it down to the top-level domain, or TLD servers. The TLD points to the authoritative name server, where the resolver finally extracts the A record, providing the final IPv4 destination address. This layered, decentralized architecture ensures that no single machine holds all the world's answers. By spreading administrative control across millions of servers, the system can scale to billions of devices without buckling. Repeating this entire route to authoritative journey for every single image, script, and link requested by billions of users would instantly overwhelm the global infrastructure. To prevent this, DNS uses caching. Once the local resolver gets a successful answer, it stores that IP address in its own memory. The next time someone asks for that site, the resolver provides the answer immediately. But these memories aren't permanent. Every record comes with a time to live, or TTL, a strictly enforced expiration timer set by the authoritative server. As shown here, the TTL determines when a cached entry disappears. A long TTL reduces the load on top-level servers by avoiding requeries, while a short TTL ensures that if a website's address changes, the update is reflected across the internet quickly. Caching is the mechanism that makes browsing feel instantaneous. By keeping answers local and skipping the journey through the hierarchy, it masks the vast geographical distances between network servers. Traditional DNS was engineered for a trusting network environment. It transmits data using UDP, a fast protocol that sends information in unencrypted clear text without requiring a formal connection handshake. Because there is no handshake to verify identity, an attacker can forge a response. If they can predict the request and send a fake packet back to the resolver faster than the legitimate server, the resolver will accept it. This is DNS cache poisoning. The resolver accepts the forged IP and stores it in its cache, believing it came from a legitimate source. Once poisoned, the user is silently redirected to a malicious server because the resolver memorized this fake mapping. This design prioritizes speed and efficiency over authentication. By relying on immediate caching and unverified packets, the same systems that make the web fast provide a direct entry point for forged data. To defend against these attacks, engineers built DNSSEC. It adds digital signatures to DNS records, allowing a resolver to mathematically verify that an answer is authentic. In this trust hierarchy, each zone is cryptographically linked. An authoritative server signs the record with a private key, creating a digital signature, locking out the evil server. The resolver uses a public key to decrypt and match hash values, proving data authentic and intact. While DNSSEC guarantees that the data hasn't been forged, the query itself is still visible. Any eavesdropper on the network can see exactly which domains you are looking for. Modern encrypted DNS protocols, like DNS over HTTPS, solve this by wrapping the entire query inside a secure TLS tunnel. This hides the packet's destination from everyone except the user and the resolver. These layers of caching, cryptographic signing, and encrypted tunneling have turned a simple directory into a hardened infrastructure. one capable of securing a global digital economy.